Welcome to Chapter 5, Fire Behavior. In 2016, public fire departments in the United States responded to 1,342,000 fires. Those incidents resulted in 3,390 civilian fire deaths and 14,650 civilian fire injuries. Fire behavior isn't an academic topic, it's life and death for the public and for us. Fire itself is a chemical reaction called oxidation. It's the same process that causes metal to rust, only fire is oxidation happening much faster and releasing far more energy. That rapid reaction produces heat and light, and once it starts, it will continue as long as fuel, heat, and oxygen remain available. Fire needs heat to start, which we call an ignition source, and that heat can come from a variety of different places. One is mechanical heat, where friction produces heat as objects rub together, like a seized bearing or a belt slipping on a pulley. Another is chemical heat, which is released or absorbed when chemical bonds are made or broken. Some reactions release enough energy to ignite nearby fuels. We also have electrical heat, created when resistance is encountered in a conductor. Loose connections, overloaded circuits, or damaged wiring can all generate enough heat to start a fire. Every fire requires fuel, but it's important to understand that only vapors burn. Liquids and solids don't burn in their original state. They must first heat up an off gas, producing vapors that can ignite. For solid fuels, this process is called pyrolysis. As the solid heats, it breaks down chemically and releases combustible gases. Those gases mix with oxygen, and that's what actually burns. So when you see a solid object on fire, you're not watching the solid burn. You're watching the vapors produced by pyrolysis burn. Recognizing this helps you understand how fuels ignite, how they spread fire, and how heat drives the entire process. For a fire to start and continue burning, four things must be present. First is fuel. We need something that can burn. Second is oxygen, because fuels must react with oxygen for combustion to occur. Third is heat, which initiates the reaction and keeps it going. The fourth element is the sustained chemical reaction. This is what keeps the fire from going out once it starts. If any one of these four components is removed, fuel, oxygen, heat, or the chemical chain reaction, the fire will collapse. This is the fire tetrahedron, and it explains both how fires start and how we put them out. When fuels burn, they produce several key products of combustion. The first one is heat, created by the rapid chemical reaction of oxidation. This heat drives pyrolysis, spreads fire, and increases the intensity of the incident. Fire also produces light. As temperatures rise, the heat energy excites electrons in the burning material, and when those electrons drop back to a lower energy state, they release visible light. These are the flames that we see. The third major product is smoke. Smoke is a mixture of unburned particles, vapors, and gases released as fuels break down. It contains a wide range of chemicals, many of them toxic, and its color, density, and movement tell us a great deal about fire behavior and conditions inside the structure. Smoke is not just a visibility problem. Smoke is fuel. It contains a wide range of flammable gases. These gases are what are actually burning during flashover and rapid fire growth. Smoke also contains partially burned solid particles, which is why it appears black and thick. Those particles are unburned fuel suspended in the air. So when you walk into a room full of smoke, understand that what you're really looking at, a room full of fuel. And because heat rises, that fuel is collecting and superheating at the ceiling level. That's a setup for a very bad day. Rollover, flashover, or rapid fire event that can kill you in seconds. Treat smoke with the same respect that you treat open flame. It's fuel waiting for the right conditions to ignite. Smoke is full of hot, toxic gases, and every one of them is deadly. Some of the most common are carbon monoxide, hydrogen cyanide, formaldehyde, and hydrogen sulfide. These gases are produced as modern fuels break down and burn. All of them are invisible, and all of them can kill you quickly. Carbon monoxide displaces oxygen in your bloodstream. Hydrogen cyanide shuts down your body's ability to use oxygen at the cellular level. Formaldehyde and hydrogen sulfide are highly toxic irritants that damage the respiratory system. When you're in smoke, you're in a toxic chemical environment. This is why SCBA use is non-negotiable even in light smoke or overhaul conditions. Smoke solids. As solid fuels heat up, unburned pieces of the fuel break away and are carried upward by the rising air currents. These particles are the same material as the original fuel. The only difference is that now they have far more surface area. Increased surface area means they can ignite much faster and burn much more intensely once they reach the right temperature and oxygen mix. This is why smoke is so dangerous. It's full of tiny superheated fuel particles just waiting for the right conditions to ignite. Heat will always move from a hotter object to a cooler object until both reach the same temperature. On the fire ground, this movement of energy is measured as heat release rate, which is the amount of energy flowing per unit of time, typically expressed in BTUs per minute or in watts. Heat transfers in three primary ways. Radiant heat travels in waves through the air and can ignite fuels without direct contact. Convection moves heat through air currents, such as winds or rising hot gases inside of a structure. Conduction occurs when heat travels along an object, like metal pipes, rebar, or other structural components. We're going to look at the three primary methods of extinguishing a fire, and each one targets a different part of the fire tetrahedron. The first is reducing the temperature of the fuel. Water is extremely effective because it absorbs large amounts of heat as it turns into steam. When we cool the fuel below its ignition temperature, the fire can't sustain itself. The second method is oxygen exclusion. If we remove or limit oxygen, the chemical reaction stops. In the fire service, this usually means shutting off as much air as possible, closing doors, controlling ventilation, or using foam to blanket the fuel. Now, when we blast it with water, we are also blocking usable oxygen from contacting the fuel. The third method is fuel removal. If we eliminate the fuel source, the fire has nothing left to burn. This includes shutting off valves for gas or liquid fuel fires or removing unburned materials from the fire's path. Every extinguishment tactic we use ties back to one of these three principles. Fires are divided into classes based on the type of fuel it's burning. This classification system helps us choose the correct extinguishing method and the correct extinguisher. Fire extinguishers are labeled using the same class system, so the class of fire determines which extinguisher is appropriate. It's important to remember that the class of fire can change as the incident progresses. A simple Class A fire in ordinary combustibles can become a Class B fire if flammable liquids become involved. Or, let's say, a Class C fire if energized electrical equipment becomes part of the problem. Now, if we're able to de-energize the Class C fire, we can now be back to a Class A fire because the only things burning are the insulation and plastic components. All right, so Class A fires involve ordinary combustibles. These are things like wood, paper, rubber, synthetics, and cloth. These are the everyday materials you're surrounded by at home, at work, and on the fire ground. And remember, you are a Class A fuel. Your gear, your clothing, and your body all fall into this category. That's why thermal protection and good fire behavior awareness matter so much. An easy way to remember is A is for average, the average everyday products you encounter constantly. These fuels ignite easily, burn hot, and produce large amounts of smoke and toxic gases. Class B fires involve flammable liquids and gases. These involve fuels like gasoline, kerosene, propane, methane, alcohol, and butane. These materials ignite easily, burn rapidly, and can produce explosive fire behavior when vapors accumulate. A key characteristic of Class B fuels is that when liquids get hot, they boil. And when they boil, they produce more vapor. More vapor means more fuel in the air, which increases the fire's intensity and spread potential. An easy way to remember it is B is for boil, flammable liquids and gases that produce vapors capable of ignition. Class C fires involved energized electrical equipment. The key word is energized. Electricity doesn't burn, but it can heat, arc, and ignite nearby materials, and it prevents us from applying water safely. If you can de energize the equipment, the electrical hazard is removed, and what you have left is a Class A fire and the surrounding combustibles. A simple way to remember is C is for current. As long as electrical current is present, it's a Class C fire. Remove the current, and the fire class changes. Class D fires involve flammable metals. These are metals like magnesium, aluminum, potassium, and titanium. These metals burn at extremely high temperatures, react violently with water, and can produce intense sparks, explosions, and molten metal flow. If you encounter one of these fires, understand that you're in for a serious challenge. These incidents are notoriously difficult to extinguish and require specialized dry powders designed specifically for metal fires. A simple way to remember it is D is for devil, because if you run into flammable metal fire, then you may have a devil of a time putting this one out. Class K fires involve organic fats and cooking oils, the kinds used in commercial and residential kitchens. These fuels behave very differently from Class B flammable liquids. Cooking oils reach extremely high temperatures. They auto-ignite easily, and they can reignite even after initial knockdown if they're not cooled properly. We encounter these fires almost exclusively in kitchens, which makes them a high-risk, high-frequency problem in both homes and restaurants. A simple way to remember is K is for kitchen, the place where hot oils, deep fryers, and cooking equipment create the perfect conditions for a Class K fire. Whether a fire starts, grows, or fails to ignite depends on several key combustion factors. The first is the type and quantity of fuel. Different fuels ignite at different temperatures, release different amounts of energy, and burn at different speeds. Next is the surface to mass ratio. Fuels with more surface area ignite faster because heat can penetrate them more easily. Fine fuels burn quickly, large, dense fuels burn slowly. The amount of oxygen available also controls combustion. More oxygen means faster, hotter burning. Limited oxygen slows the reaction and can create heavy toxic smoke. The environment matters as well. Temperature, humidity, wind, and ventilation all influence ignition and fire growth. You also need an ignition source, something that provides enough heat to start the reaction. Finally, the orientation of the fuel to the heat source affects how quickly it ignites. Heat rises, so fuels above a heat source ignite faster than fuels beside or below it. Fire progresses through four distinct life stages, and each stage tells us how the fire is behaving and what it needs to continue. The incipient or ignition stage. This is the beginning of the fire. Heat, fuel, and oxygen have all come together, and the chemical reaction starts. The fire is small, confined to the original fuel, and producing relatively low temperatures. The threat is minimal, but the environment is already changing. The growth stage. Now the fire begins to intensify. It consumes more fuel, produces more heat, and starts influencing the space around it. Ventilation, fuel placement, and surface types are all playing major roles right now. Thermal layering forms, rollover becomes possible, and the conditions for flashover develop quickly. Fully developed stage. This is the peak of the fire's energy output. The fire is ventilation controlled, pulling in oxygen and pushing out superheated gases. Temperatures are at their highest, structural integrity is compromised, and conditions are immediately lethal. This is the most dangerous stage for firefighters. The decay stage. The fire enters decay when it runs out of fuel, heat, or oxygen. Temperatures begin to drop, but hazards remain. Toxic gases, weakened structure, and the potential for reignition if oxygen is suddenly reintroduced. The fire is dying, but the environment is still hostile. We're going to go through each stage of fire in a little more detail. Some of this will sound repetitive, but that will just help us remember it. The incipient stage is the earliest stage of a fire. It begins the moment where there is enough fuel, oxygen, and heat, along with an ignition source, to start the chemical reaction. At this point, the fire is small and confined to the original fuel that is ignited. Temperatures are still low, heat production is limited, and the fire has not yet begun to significantly influence the surrounding environment. In this stage, the overall threat is minimal, but this is temporary. Even a small flame is already heating nearby fuels, producing smoke, and setting the conditions for rapid growth, even if nothing interrupts the process. The growth stage is where the fire begins to gain real intensity. Heat production increases, flames extend, and the fire starts influencing the environment around it. At this point, the fire is no longer controlled by the original fuel alone. It becomes highly dependent on environmental factors. Ventilation plays a major role. Any opening, a door, a window, a crack, or a ventilation action can dramatically accelerate fire growth by feeding it oxygen. The placement and configuration of fuels also matter. Vertical fuels ignite faster. Fuels stacked or closely spaced allow heat to transfer more efficiently, speeding up fire spread. Even the type of surfaces involved affects fire growth. Smooth, synthetic, or highly combustible surfaces often gas quickly and contribute to rapid fire development. In the growth stage, the fire is building energy, expanding its footprint, and setting the conditions for flashover if nothing interrupts the process. In the growth stage, the fire begins shaping the environment, and the environment is also shaping the fire. One of the first things we see is thermal layering. Hot gases rise and form layers based upon their temperature and density. The hottest, lightest gases collect at the ceiling, cooler gases settle a little lower. And remember, all those gases are still fuel. They're full of unburned hydrocarbons, flammable vapors, and superheated particles. That overhead layer is not just smoke, it's a fuel rich environment waiting for the right conditions to ignite. One warning sign is rollover. Rollover is the spontaneous ignition of these upper gas layers. You may see small tongues of flame or even a flicker of what looks like lightning in the smoke right before ignition. Rollover tells you the environment is reaching critical temperatures and the flashover is becoming possible. Then there's the flashover itself. This is the point where everything in the room is superheated and all exposed surfaces ignite almost simultaneously. At around 1150 degrees Fahrenheit, even carbon monoxide burns, and the air itself has now caught on fire. This is the moment when survivability collapses. Once flashover occurs, your life expectancy is about 6 seconds. Not 6 minutes, 6 seconds. No PPE, no training, no experience can overcome that environment. The only winning move is to recognize the signs early and stay out of the conditions that lead to it. The A backdraft occurs when you have a compartment filled with superheated, fuel-rich gases that don't have enough oxygen to burn. The fire has been choking, smoldering, and building pressure. The heat is still there, the fuel is still there, the only thing missing is oxygen. When that compartment suddenly gets oxygen, the entire mixture can ignite explosively. This usually happens when somebody opens a door, breaks a window, or otherwise creates a fresh air opening. The fire doesn't just flare up, it detonates. Backdraft conditions are some of those violent events you can encounter on the fire ground. Indicators indicate pulsing smoke, smoke stained windows, and air being drawn inward, and a building that looks like it is breathing. If you force the wrong opening at the wrong time, you can trigger the event yourself. Rapid fire growth is when a fire moves very quickly from the incipient stage through growth stage and into the fully developed stage, sometimes in a matter of seconds. The fire doesn't follow the slow, predictable curve that we like to teach. Instead, it accelerates violently. This kind of rapid escalation is often the result of a backdraft type event. You have a compartment full of hot, fuel rich gases that suddenly gets oxygen. When that oxygen hits, the fire doesn't just grow, it erupts. Rapid fire growth can push a room into flashover with almost no warning. One moment you're reading smoke and heat, the next moment the entire environment lights off. These are the conditions that kill firefighters who are inside or too close when the environment transitions faster than they can react. The fully developed stage is the point where the fire is free burning and producing its maximum heat release rate. At this stage, the fire is consuming the greatest amount of fuel it can reach, and the environment is at its most hostile. Temperatures are extreme, visibility is zero, and structural integrity is rapidly deteriorating. A fully developed fire may become fuel limited, meaning it has plenty of oxygen but is running out of available fuel to burn. Or it may become vent limited, meaning there's still plenty of fuel and heat but not enough oxygen to support full combustion. Vent limited fires are especially dangerous because the sudden introduction of oxygen can trigger rapid fire growth or flashover. It's important to remember that not all fires reach this stage. Some are interrupted early by suppression, ventilation changes, or fuel limitations. When a fire does reach fully developed conditions, the environment becomes immediately lethal and the structure begins to fail. The decay stage begins when the fire has consumed the available fuel and oxygen inside the compartment. With nothing left to support active combustion, flame production drops sharply or stops altogether. At this point, the fire has essentially burned itself out, whether firefighters have even arrived or not. The reaction is collapsing because the fire can no longer sustain itself. I want you to remember to think about this. Did you put the fire out, or did it burn itself out and you just slowed it up a little bit? Decay does not mean safe. The environment can still contain superheated gases, toxic smoke, hidden embers, and structural weakening. A sudden introduction of oxygen, such as a door opening, a window failure, or even our own ventilation, can still trigger reignition and even a rapid fire event in the right conditions. In the vent limited decay stage, a fully developed fire has run out of oxygen, not heat. The compartment is still packed with superheated gases and superheated fuels, and there is plenty of both. Combustion slows or stops, but the environment remains extremely dangerous. Even though visible flame may be minimal, pyrolysis continues. Fuels are still breaking down, still off gassing, and still adding more fuel vapor to the hot upper layers, just at a slower rate. This is the trap. The fire looks like it's dying, but it's actually just waiting. A sudden introduction of oxygen, an uncontrolled vent, a window failure, or even a firefighter opening a door can instantly drive the fire back into fully developed conditions. BLEVE, which is a boiling liquid expanding vapor explosion, happens when a pressurized fuel vessel fails and releases all of its vapor instantly. The liquid inside the tank rapidly boils, the vapor expands violently, and the tank shell can launch hundreds or even thousands of feet. This is why BLEVEs kill firefighters who are anywhere near the hazard zone. The only way to prevent a BLEVE is to keep the container as cool as possible, especially the vapor space. Continuous cooling buys time, nothing more. Get on this thing early with hose lines. If you can get a ground monitor in it, then that is ideal because you don't have a person standing there. If you see flame impingement on a pressurized tank, hear venting, or see discoloration or deformation, the correct action is simple. Evacuate. Get distance, get behind cover, and protect exposures. You cannot out-train or out-gear a BLEVE. Distance equals survival here. When we talk about reading smoke, the first rule is simple. The behavior of smoke is more important than the color. Color can help, but movement, volume, velocity, and pressure tell you far more about what the fire is doing. House siding, engineered woods, home furnishings, all of it is made with petroleum products now, so it's all black. Light, wispy smoke usually means minimal current building. The fire may be in the incipient stage, or it may be smoldering with low heat production. It's not pushing hard because the energy just isn't there yet. Heavy pressurized smoke tells a different story. When smoke is thick, fast moving, and under pressure, it indicates significant combustion and a fire that is producing a lot of heat. Pressurized smoke means the fire is working hard somewhere, even if you can't even see the flames yet. When dark smoke turns gray or white, that's a strong indicator that water is hitting the fire. The color shift comes from the steam production and cooling of the fuel package. It's one of the best real-time feedback tools that we have in the fire service. And remember this, reading smoke is an art. It takes time, repetition, and experience. We can't just teach this in a book or a slideshow. The learning process here never ends. Every fire teaches you something new if you're paying attention. We have reached the end of the fire behavior chapter. If you have any questions, please reach out to myself or one of your other instructors. I thank you for your time.